So what did we do last time? We saw, you've seen that when we have a matrix Lie group, we have the corresponding Lie algebra. And last time we have seen this corollary, which is very nice. So we have our matrix Lie group. Then we have Lie algebra, G. And then the geometric meaning, we have a geometric meaning for this. So when we have, so G is a manifold, we knew that G is going to be a manifold. And identity element is there, and the Lie algebra is the tangent space of the Lie group at the identity. That's what we learned last time. And there are more connections between Lie algebras and Lie groups. And we will see a few of them. So if G is connected matrix Lie group, then for all A, for every element in G, we can write A as the product of exponents of elements in Lie algebra. It's not always possible to write this as a single exponent, but if you allow yourself to make a product with them, then it's always possible for some x1 x n in G. All right, and so let's recall that if we have a Lie group homomorphism, then this determines a unique Lie algebra homomorphism. Okay, so here this G, Gothic G, is the Lie algebra of Lie group G. This H is the Lie algebra of H. So whenever we have a Lie group homomorphism, capital Phi, then there is a unique Lie algebra, corresponding Lie algebra homomorphism like that. But the converse is not true in general. So there might be two different Lie group homomorphisms which give rise to the same algebra homomorphism. However, if G is connected, then they are one-to-one. Phi is determined by Phi. That means there is a one-to-one correspondence. So if you understand Lie algebra homomorphisms, then you can understand Lie group homomorphism and vice versa. So if G is connected, studying Lie algebra homomorphism is more or less the same as studying Lie group homomorphism. Okay, and also we have seen that, recall, if G is commutative, then we know that its Lie algebra is also commutative. But the converse is not true in general. But again, if G is connected, then they are if and only if commutative, if and only if G commutative. And finally, if G is a matrix Lie group, then we know that, so this denotes the identity component, the connected component containing the identity. It turns out that this is also a matrix Lie group. So this component is matrix Lie group. So because it's a matrix Lie group, we can talk about the corresponding Lie algebra, and it's the same as the Lie algebra of G. And moreover, so that's the Lie algebra of G is the same or isomorphic to Lie algebra of, they are the same, of the identity component. So because of this correspondence between Lie algebras and Lie groups, you can study just one side, and that will be pretty much enough. And Lie algebra, it turns out that Lie algebra, they are easier to understand than Lie groups, at least in our point of view. So we will, from now on, we will be mostly focusing on Lie algebras instead of Lie groups. Okay? All right, so that's for chapter 3. Now we're going to move on to the next chapter. So chapter 4 is about representation theory, so basic representation theory. All right, so what is that? What is a representation? So we have to define them first. Representations. The definition is actually very simple, very short. So V is a finite dimensional vector space. And we will, from now on, we will almost always, I think almost, we will only consider C as the base field, So unless otherwise mentioned, it will be always over C, because C is algebraically closed and everything is nicer in C. So, and general linear group GL of V is the group of invertible linear maps, linear transformations on V. So it's a map, linear map, invertible from V to V. So if you specify a basis, then it will be GL and C. Or if you, it's really a GL and C in another notation. And we also have this GL, lowercase GLV. This is really the same as sometimes written in this way, end of V, this set of all endomorphisms. So it's a space of all linear transformations on V. So it's not necessarily invertible. So this as a set or as a space contains this part. And this becomes Lie algebra if you define Lie bracket in the usual way. So this is a Lie algebra with bracket given like this. So where this multiplication here is a composition of maps. So X and Y are linear transformations, so we can compose them and we can subtract them, etc. So this is a linear transformation on V again, so this is well-defined map. And this gives us, this makes GLV a Lie algebra. So basically, so this is a Lie group. This is a Lie algebra. This will be, how can I say, easiest or standard, most standard Lie group Lie algebra. So these are things that we can kind of understand. So for other Lie algebra or Lie groups, we will relate them with this. Okay? We want to understand something else, some other Lie algebras in terms of this, in some sense. So that's the definition. That could be a motivation for this definition. So now G is any matrix Lie group. And a finite dimensional representation. It's a complex, but we will always assume that's a complex representation. I'm going to just simply write representation of G is just a Lie group homomorphism. Say capital pi from G to our favorite Lie group, GLV, for some vector space V, where V is some finite dimensional vector space. So definition is really simple, just a homomorphism, Lie group homomorphism, that's all. And what about Lie algebra, representation of Lie algebra? It's the same. G is a Lie algebra. A finite dimensional representation of G is a Lie algebra homomorphism. So denoted pi from G to our favorite Lie algebra, GLV, for some finite vector space V. Yeah, so definition is really simple, so I guess there should be no problem understanding this definition. Just a map or homomorphism. And I think, so if this map or this is one-to-one, then this representation is called a faithful. So let me write that down. So if pi is one-to-one, we say that the representation is faithful. So it's a faithful representation, one-to-one map. So if it's faithful, then let's go back to this definition. If this is a faithful representation, this can be considered as an embedding inside this. So somehow this one, invertible linear transformations, or if you fix a basis, it's going to be just a matrix. So in this way, we can understand matrix Lie group as just a matrices, because it's inside here. Same here. If this is a faithful representation, then this can be considered as an embedding here. So basically, what's going on here is Lie algebra, sub-algebra of this. That's one way to maybe understand that the definition of representations, but there is another way of understanding these representations. So we will often consider our representation as a linear action on a vector space. Okay, what does that mean? So you should really think of this as an action, some kind of. So linear action means a linear action. What do I mean by that? Is kind of let's say G on V means a map, G cross V to V, like, but usually denoted by G dot V. So it's a map. It kind of acts on V. That means it kind of receives V and then it turns it to another vector, something like that. So kind of action. But linear means it respects the linear algebra. Linear or vector space. It respects all the axioms of the vector space. So such that G dot Cu plus dV should be equal to where C, D, complex numbers, U, V, vectors, C times G, U, D times G, V, something like that. Of course, this is scalar multiplication. This is the action. So, for example, how can you understand representation as an action? So we have a representation G to GLV. So it's a homomorphism. This means for each element in our group G, we have pi of G, which is, of course, inside this GLV. But what is this? This means it's a linear transformation or invertible linear transformation. So this means pi of G, this is a map from G to V to V. So that means it sends an element here to an element here, which is, of course, pi G of V. Because it's a linear transformation, it will be another vector. But we will think of this as a action. We will write, instead of pi of G of V, in this way. G dot V, because it's simpler. You know, we don't have to write capital pi or this parentheses. If there are many parentheses, it looks complicated usually. So instead of this, we will, because we assume that we understand this representation. So once this is given, we will simply write this way instead of writing like a pi all the time. Sometimes, if necessary, we will write pi, but usually we will think of this as an action and then simply write this way. So, so representation theory, but just the name, if you look at the name, the representation means we really represent something. So we have a group. So what is a group representation? We represent group as something, but that something is a matrix. So we can understand group elements as matrices. So a group element is represented by a matrix. I think that's why the name is representation theory. But representation theory is not all about just representing groups or algebras. I think it's more to. I think there's more to this action. So I want to compare this with real life understanding. So group, suppose that we want to understand the group. How can we understand the group? We can just look at just group itself. We can understand a little bit. But instead of understanding group itself, we will look at how this group acts on something else, like a vector spaces. So for instance, suppose you want to understand someone in this room, maybe Im Dong-sun. Suppose we want to understand Im Dong-sun. Of course, we can understand just by looking at himself and maybe his background or his some physical data, etc. But we can also understand him maybe we feel that we can understand him better if you can see how he interacts with other people, how he interacts with some or object or animals or other people. That way we feel like, oh, we understand him better. So representation theory is something like that. We just don't look at the group or algebra itself, but we look at how this group or algebra interacts with a vector space. That's, I think, a philosophy of representation theory. Okay? So, but it's kind of, if you look at this definition, and it's kind of abstract. So, but we will see more and more examples. So if you look at more examples, then you will have a better understanding of this. But I think for the first lecture today, I think could be a bit difficult to digest. But hopefully later you will understand better. Okay, let's say, oh yeah, note. So this GLV is a group representation. Group representation means just a group homomorphism. And what does that mean? It means GH equals GH, right? Oh, sorry. Of course, that's true. Yeah, it's like that. And in terms of group action, this means GH, if this acts on V, it must be equal to G dot H dot V. So group action or group representation is basically linear action with additional condition like this. Linear action means it's an action respecting the vector space structure, and group homomorphism or group representation is a linear action with additional condition like that. What about representation of a Lie algebra? So this is a representation of a Lie algebra. So in other words, it's just a Lie algebra homomorphism. And it means we have a Lie bracket structure for elements here. And this must be equal to this. It must respect the Lie algebra structure. But this bracket is a bracket inside GLV. But that, we know what that is. So pi x, pi y minus. Because these are linear transformations, we can kind of multiply them, or yeah, this is the multiplication and as composition. And can we write this as an action? So x comma y is if this acts on V, this must be equal to this acting on V. But what is that? So let's write this way. Yx acting on V. But basically what this really means is x dot y dot V minus y, we don't need that, y dot x dot V. So Lie algebra homomorphism or representation of a Lie algebra is a linear action with this condition. That's another way of considering. But here, this is multiplication as linear maps. We don't have multiplication like this inside G. This could be a little confusing. But this one is multiplication in as this means a composition like this. Okay. So today we will define some terminologies related to representations. Okay. Mostly the definitions for Lie algebras and Lie groups, they are almost parallel. but we have one exception, but we will see that later. So let's say capital pi is a representation of G. We will sometimes write like this, acting on V. This means pi is a group homomorphism from G to GLV, because GLV, that's a representation, so we can understand this as a group action on V. And okay. So this is a vector space. A subspace W of V is called invariant. If G dot W is inside W for all G in G. Okay, so what does this mean? This means set of V dot W for all W in W. So we have elements here. For every element, we apply G, and then there will be some vector. You collect them all. If everything is inside W, then we say that it's invariant. Does not go outside. It stays just there, inside this W. And an invariant subspace W is non-trivial if it's not empty, if it's not the whole set. So yeah, this means it's not the space with only zero. Yeah. So I will simply write this way, but technically it means this. All right. And a representation is irreducible if 0 and W, oh no, not W, 0 and V are the only invariant subspaces. In other words, there are no non-trivial subspace, invariant subspace. No non-trivial, the same. Invariant subspace. The same thing. They mean the same thing. Okay. And of course, I define this for just a representation of a Lie group. The same thing, same definition works for representation of Lie algebras. So we can talk about invariant subspace or irreducible representations, etc. for group representations or Lie algebra representation. Okay, and I will go to the next page. All right, again, let's say capital pi is a representation of G on V, acting on V. I'm simply writing that way. And let's say a sigma representation of G on W. Or sometimes we say we just say V is a representation. Sometimes we say V is a representation of G without even writing this. But that means we have a group action on V that is somehow specified. So in that case, we say it's a V. Just vector space is a representation. Of course, we know how the action is defined. But anyway, we have two representations of G. A linear map, say phi from V to W is an intertwining map. If phi G dot V equals G dot phi of G for all G, for all V. Okay, what does that mean? You can understand this using diagram. Let's do that. So we have V and W. There is a map, linear map, like phi, like that. And V is a representation. So we have a G action. So for every G, we can multiply G on V. Then we have G dot V, which is an element here. So it's going to be a map, linear map from V to V. Again, this also acts on W. So we have G dot map, this action, sending an element in W to an element in W. This means this diagram commutes. So you can exchange the order of phi and G. And if phi is invertible, then it is called an isomorphism. Isomorphism of representation. Okay. And if, in this case, if there exists isomorphism phi from V to W, then we say that V and W are isomorphic. And of course, we write V isomorphic to W like that. So if these two representations are isomorphic, then everything, the action here can be translated to the action the other side. So that's what really matters for our point of view. So we will only, if two representations are isomorphic, we will really think of them just the same representation. So we have learned two important concepts, irreducible and isomorphic representation. So typical problem in representation theory is to classify all irreducible representations up to isomorphism. So we have given a group or a Lie algebra, and the question is, what are the irreducible representations of this? That's one typical problem. Okay. So we have, okay, oh yeah, I didn't mention this, but of course, it's the same for representation of Lie algebra. We can talk about the same thing. Intertwining map between Lie algebra representations and two representations are isomorphic in exact the same way. Okay. Okay. So we have representations of a Lie group or Lie algebra. So what are the connections between them. We have this proposition actually for free matrix Lie group with Lie algebra G. And let's say capital pi is a representation. So representation of G. Then there exists a unique representation pi of Lie algebra G to general linear group of G such that e to the x equals e to the for all x in G. Moreover, equals we can actually compute the representation in this way. And also I think this should be capital pi and then small pi and this big pi A inverse for all x in G, for all A in G. Actually, we have the same proposition for two Lie groups G to H. This is just a restriction. We just restricted that to GLV. But if this is GLV, that's a representation. That's by definition. So we just copy all the proposition statements from the previous proposition in this way, then it works. So if you have, this means if you have a representation of a Lie group, then we have a unique corresponding representation for the Lie group. And proposition, if G is connected matrix Lie group, and again, of course, with Lie algebra G, then first, we have representation of a Lie group. This is irreducible if and only if the corresponding Lie algebra representation is irreducible. And second, two representations are isomorphic. Group 2 representations of a Lie group G is isomorphic if and only if their corresponding Lie algebra representations are isomorphic. So in this case, classifying irreducible representations are really the same in Lie algebra side or Lie group side and Lie algebra side. So we will be focusing on later Lie algebra because of this. Okay. And now, yeah, I only talked about just the general definition, so I'm going to give you some examples. Some typical examples, so you will see them quite often, I guess. Matrix Lie group. So G is a matrix Lie group, then G is by definition a subgroup of GLN. It's a closed subgroup of this, right? It's GLV. So it's already a subgroup of this. And the inclusion map, so G is, because it's a subgroup, it's already there. This is a representation. This is called the standard representation. So, okay, G. So yeah, in this case, you can think of the G as Cn, let's say. Then G acts on V, right? Because A dot V is just A times V. If it's a matrix, it's here, so it's a matrix or a linear transformation. It sends a vector to another vector. It's already, action is already defined. So there's nothing to do. It's already there. And if Lie algebra is if this is subset of matrix algebra, then this is, if this is a Lie algebra of matrices, then the standard representation is again just inclusion. This is already a matrix, so it acts on C to the n, so it's the same as before. Yeah, not very interesting. All right. Another not very interesting example is trivial representation of G is a map or homomorphism from G to general linear group like this. But so the dimension is 1 or the degree 1, where pi of A is just identity. It satisfies all the axioms that have to be satisfied. So G acts on V in this case, V which is just C. So the question is this representation irreducible? Is this irreducible? So trivial representation is a representation acting on V, which is of dimension 1. So what is the definition of an irreducible representation? Does not have any non-trivial invariant subspace. Is that true? It doesn't even have any non-trivial subspace because it's dimension 1. Subspace is just 0 or the whole set, whole space. So it's a clearly irreducible. No non-trivial invariant subspaces, but doesn't even have any subspace, non-trivial subspaces. So trivial representation is an example of an irreducible representation. Okay, what about the trivial representation of a Lie algebra? That's not exactly the same. So let's talk about that. So the trivial representation of a Lie algebra G is like this. G to GL1C, where we define pi of x to be just 0 map instead of identity. Then again, is this an irreducible representation? Yes, it's acting on a vector space of dimension 1, so it's again irreducible because acting on V, which is of dimension 1. You may wonder why do we have to set this to be 0 instead of the identity as before? So if we try to define pi of x to be the identity as before, then it's not a Lie algebra homomorphism. Then pi is not a Lie algebra homomorphism. So we have to really say it's a 0. Do you see why? Yeah, think about it. You can check. All right. So we've seen standard representation and trivial representation. This one is will be very important in our study. G is a matrix Lie group with Lie algebra G, and the adjoint representation. In fact, we have already learned this. We only said there's a map, but now we can say there's a adjoint representation. Is add AD from general linear group of this. This is a vector space, so we can talk about this. And the adjoint representation of G is, as you expect, small AD, general linear group AD. Of course, here the definition, if you want, this gets sent to AD sub A, right? I'm not sure if this is really a remainder. I think I should recall what this is. ADA of B equals what? It's a conjugation by A, so it's B, A inverse, and here ADX of Y is defined to be X comma Y. So that's how we define these adjoint maps. We only call them like adjoint maps, but they are really representations, so we now call them adjoint representation. So, okay, add is a representation. This means representation of groups, of course. This means add AB equals add A times add B, but we have checked this already. And add is a representation of Lie algebra. That means add X comma Y is equal to add X, add Y minus add Y, add X, but we have already checked this before. So these, they will play a very important role in when we study representation. Any questions so far? Yeah, today's lecture will be a bit abstract, but next lecture you will see a concrete example. 4.3, new representations from old. So yeah, it's a natural question. How can we make more complicated representations by using simple ones? G, matrix Lie group, pi 1, pi 2 representations of G on, say, V1, V2 respectively. So this is a representation acting on V1, this is a representation acting on V2, and the direct sum denoted pi 1 direct sum pi 2 is the representation of G. So we make a new representation acting on. So the direct sum of these vector spaces, V1 direct sum V2. We have to define the action, right? Via the action. So element here can be written as a like a pair component, just component-wise action. We already, because V1 is a representation, we already have an action there. So it's action. This is an action for V1. This is an action for V2. Yeah, notice that I didn't even use pi 1 and pi 2. But if you really want to use this, then I think you should write, or if you want to use this, because this is a map, we have to define what this is. This is, or V1 comma V2 equals pi 1 of G of V1, pi 2 of G of V2. Their meaning is the same, but maybe it's better if I use A, because I used A here. That will make additional complication. So they really mean the same thing, but yeah, this is looks simpler, so we will keep to this notation instead of writing this parentheses all the time. All right. And direct. So now we talk about. We can talk about Lie algebra and pi 1, pi 2. Defined exact same way. All right. So for direct sum, they are defined the exact same way. All right. Now, next, tensor product. I assume that you have basic knowledge on tensor product. So let's recall just only simple thing. Vector spaces with, let's say, basis u1 dot 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 um for u and v1 dot 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 vn for v. Then the tensor product, it's not really a definition, I guess, but I assume that you already know the definition. Or yeah, this is the tensor product. Then has basis. What happened? Tensor product has basis. Okay. Ui tensor Vj, where I is from 1 to n, m, j is from 1 to n. So basically, it's a space spanned by objects like this. All right. And if F is a map, linear map, G is a map from V to V, if these are linear maps, they are tensor product of maps. Is well defined, and it's a map from, is denoted F tensor G, V, with such that satisfying. So U tensor V, it sends everything to this. So we can talk about the tensor product of maps. So now it's time to define the tensor product of representations. So how can we define that? All right. GH matrix Lie groups. And let's say phi1 is a representation of G on U, and pi2 is a representation of H acting on V. Now, what is the tensor product of these? Then the tensor product, so pi1 is denoted pi1 tensor pi2. Tensor product of pi1 and pi2 is the representation of G times H. So, yeah, if you have two groups, you can compute this direct product. So G product H. So it's a representation of this group. So new group, so bigger one, acting on a tensor product of this. How is this acting? In the natural way, you can imagine. So just A comma B in this way. So this is an element in G times H. So this is defined, and this is defined, and this is a map. This is a map. So we can talk about the product, tensor product of the map. So it's given like that. So note that. So this means pi1, pi2 is a linear map. So representation. So it's a linear Lie group homomorphism from this to general linear group V U tensor V. Like that. So this definition looks natural for groups, but for Lie algebra, it's a little different. It's natural, like similar to kind of direct sum, but before defining the tensor product of Lie algebras, we will consider the corresponding Lie algebra, because here we have Lie groups G and H and representations. Then we can obtain Lie algebra representations out of these. And let's see what happens to this. So the proposition says that we have the same situation, matrix Lie group with Lie algebra G and H. And pi1, pi2, these are representations of G and H. So the first one is a representation of G, the second one is a representation of H. And because these are representations of Lie groups, we have corresponding Lie algebra representations. So let's say corresponding Lie representations of G and H. So these are determined uniquely by the theorem. All right. And we have already defined the tensor product of Lie representations of Lie groups. So we have this. These are the tensor product pi 1 and pi 2. This is given. The question is, what is the, so this will induce a representation of Lie algebra, right? What is that? So let pi 1 tensor pi 2, just a notation. This is, we haven't defined this tensor yet. It's just a notation. Let's be the corresponding Lie algebra representation of G Dirac sum H. If we have G, so this is a, okay, this thing is a representation of G times H. So if you have a representation of G times H, then the corresponding Lie algebra is like this. So we will get a corresponding Lie algebra representation of this. And how does it look like? Then the theorem says pi 1, how this representation acts on this x comma y equals pi 1x tensor identity I tensor pi 2y. It acts like that. The action is something like that for all x in G and y in H. So it looks different. It looks a little different. Yeah, I'm not going to prove this, but maybe you have some kind of guess why we should get something like this instead of, why do we get this instead of something more which look more natural? Why don't we get this? But why do we get this instead of this? I'm not going to prove this, but you know, this is somehow related to derivative. So when you have derivative, tensor product, some kind of product rule would be applied. So that may explain why we should get something like this. Okay, that's not a proof, of course, but if you want a proof, you can read a textbook. But maybe you can have a feeling, yeah, maybe we should get something like this instead of this. Okay. All right. So this is a proposition, and using this, we will define tensor product of Lie algebra representations in this way. Then it will be consistent with this kind of context. So, definition: G and H, these are Lie algebras. Pi 1, pi 2 representations of G and H, they acting on U and V respectively. Then the tensor product pi 1 tensor pi 2 is the representation of what? Of G Dirac sum H. Acting on U tensor V by the following rule. But the following rule is the previous rule. X comma y pi 1x identity tensor pi 2. So i.e., in terms of action, x comma y, how does this act on, say, this single tensor, u tensor v? So the first component acts on the first component here, u, and then the second component is identity, so it's v. So let's put parenthesis, and then u tensor y. So it acts like that. The action is like that. So in terms of action, you can say something like that. Oh yeah, and note that it is tempting to define pi 1. Why don't we define this way? Then what happens? As a map, it seems okay, but then it's not a representation. It does not satisfy the axioms for a representation. So it's not a representation. So we can forget about this. It's not linear at all. It's not even linear. Oh yeah, okay. So we defined, so we have two groups or two different Lie algebras, and then we had representation of one algebra, another representation of the other Lie algebra. We consider the tensor product. We can also talk about the tensor product of two representations of the same group or the same representation. So the definition is slightly different. So matrix Lie group. So pi 1, pi 2, these are representations of G acting on V1, V2. Then the tensor product denoted pi 1. Yeah, this should be capital, but okay, let's just write it. Of G is the representation. Oh, okay. Tensor product of G, instead of this, tensor product of pi 1 and pi 2 is the representation of G instead of. So before, what did we have? So pi 1 is a representation of G, pi 2 is a representation of H, but H happens to be equal to G. So if you use the previous definition, then it should be this. But instead of this, we want to consider this as a representation of G, because we can do this. Is the representation of G acting on V1 tensor V2 via pi 1, pi 2, A equals the same way. The same way. Okay. So the only difference here is that H equals, we are considering representation of a single or the same group, and instead of consider the tensor product as a representation of G times G, we can think of this as a representation of G. All right. And similarly, we can define Lie algebra representation, tensor product of Lie algebra in this way. Pi 1. I think I can just copy the same thing. So let me just write only the difference. So Lie algebra. So the same thing, representation of G. Tensor product is defined. Instead of this, we have to write pi 1, say x equals pi 1 x identity pi 2 x. So for Lie algebra, the tensor product is defined like that. Oh, no. Okay. Maybe I can talk about the dual representation. Yeah, so recall. So when we have a vector space V, vector space, we have the dual vector space. So it's a dual. So what is this? Dual of dual vector space of V, and as a space, this is a linear map, or linear functionals, or linear map from V to the base field, which is C in our case. So V star, or dual, is just a linear map from V to a scalar. Okay. Then if A is a linear map, the transposition, A transpose, is a map. We can define this transpose of A, which is the map from V, dual of V to the dual of V, defined by so we have to have an element here. We have say one element here, phi, okay? So linear map or linear functional. This gets sent to what? Yeah, it gets sent to this. But the definition is, so this is again a map here. That means it's another linear map from V to C. So we have to say what this is. This must be a scalar, but this is defined in this way. The definition is like that. All right, now it's time for the dual representation. So as before, matrix Lie group representation of G on V, the dual representation denoted pi star is the representation of G acting on B star by the following rule. Pi G inverse transpose. So G is a group, so G inverse exists, and we can talk about pi of G inverse, and then we just take the transpose. Then it is indeed a representation. And similarly, we have G represent group Lie algebra, and we have pi representation of G on the same space, say. Then this is defined like this. Pi star of X is minus pi of X is defined like that. Then it's also a representation, and it's the dual. All right, so why is this nice? Okay, so G matrix Lie group with Lie algebra G. Okay, the property is that, so pi is a representation of G, then we have corresponding representation, being a representation of G, right? Under this condition, first, I don't think we need this. All right. We don't have to have exactly this is a corresponding one. You can forget about this. Sorry about that. Any representation of these are unrelated, let's say. So the same. It's irreducible if and only if pi is irreducible. Second, pi star star is isomorphic to pi. So it has properties that you can expect from dual. Or the same for this pi, capital pi. Okay. All right. So I will stop here. So next time I will see more concrete example. All right. Thank you for your attention.